In this video, we're going to take a look here at example 1 and start to compute some partial derivatives. Now, one of the things that's going to be important to keep in mind when computing a partial derivative is what was actually happening within the pictures that we discussed at the opening. Remember that when I'm computing my partial derivative with respect to x, I thought of my variable of y as being fixed, as it being locked in. Up in the pictures, I was moving along this black curve, and I imagined then that y was locked in as a specific number. So when I go ahead and compute a partial derivative with respect to y, I'm going to take a derivative of this function, and the entire time I'm going to pretend that y is just a number. So quickly, for example, let's just suppose for the sake of argument right now that I could rewrite this function, and wherever y was, I put in a number, say like 3. So I had like 2x, and then I had like 3 to the third, and then I had 6x times a 3, and then I had minus x to the 7th. This would look like a Calc 1 function, and it would be so easy to take its derivative. I would get 2 times 3 to the third, I would get 6 times 3, and finally I would get minus 7x to the power of, not 8, sorry, 7x to the 6th, right? Because I can just follow my basic derivative rules here. So the weird part is I have to come up with the same basic final answer, except that I'm never going to fill in a specific value for the y. I'm just going to keep y in, but imagine that it's a number and treat it as such. So I would go ahead then and get a partial derivative that looks like the following. I would get 2y cubed, that's a number being multiplied to x, so the derivative should be 2y cubed. Just like over here, I got 2 times 3 cubed. Over here again, I have 6y times the variable of x, so the derivative should just be 6y. Kind of like over here, how I got 6 times 3. And finally at the back, I should get my 7x to the 6th. In much the same way, when I do a partial derivative with respect to y, I'm going to treat x like it's a number. I'm going to go ahead and imagine, when I take this derivative, that I have 2 times a number in front of a y to the third. So that should be 2 times a number times 3y squared. Similarly over here, if I have 6x times y, the derivative there should be 6x, just 6 times the other number that was the coefficient. And finally at the back, this is actually the easiest derivative of all. If I'm pretending x is a number, let's say again like the number 6, then what's the derivative of 6 to the 7th power? Well, 6 to the 7th is just some number, and the derivative of any number is 0. So here I would end up with 6xy squared plus 6x for my partial derivative with respect to y. Again, the real key, and this is kind of the weird, funky part, is you have to try to make sure that you're imagining in the partial derivative with respect to x that y is just a number, treated as such. And in the other case, when you're doing a partial derivative with respect to y, you're going to treat x like it's a fixed number. If you're able to do that, these calculations should be just as easy as derivatives back in Calc 1.